discussing our project title named Smart Energy Management Using Forecast-Driven Generation Optimization. In smart grid systems, electricity demands keep changing because of the main factors are weather conditions, time of day, and electricity price variations. However, the electricity generation needs to be planned in advance. Many conventional power systems still rely on reactive control only, where adjustments in generations are made only after demand changes occurs. This leads to fluctuations in this load. This may cause inefficient energy utilization and a higher operational cost. To address this challenge, our project uses ML model to forecast electricity load and electricity prices based on historical data and weather variables and time related features. We have used initially 1 hourly using 1 hourly data. Later we updated it as 15 minutes interval data to capture short term variations in electricity demands. For example, if you take hourly data, then if hour to hour maybe a small change will be there. But if in a half an hour, if a fluctuation happens, then it can't manage. That's why we reduced our time interval data is 15 minutes data so that we can capture short term variations easily.
I will be talking about model architecture. Our base idea was to use a deep learning model such as CNN plus LSTM to do the load forecasting prediction. But under faculty's guidance and thorough understanding of the dataset, we changed the model architecture as follows. Here, we are doing the pre-processing step for all the features in the dataset, and using the sliding window approach, we are giving the data to the model. Here, we are following parallel tracks where each track is an ensemble stack approach. Because if we train a global model on load forecast patterns and solar forecasting patterns, wind forecasting patterns, it will be difficult for the model to understand all these and provide a proper output. So it will reduce the accuracy of the model. So to make the model more robust, so we are following three different tracks here. Since I already said that each track follows an ensemble stacking approach, the base models here are trained independently and they explain about the patterns of the data and predict accordingly. Here we are using a out of fold predictions because for the meta model here doesn't learn on patterns, but it learns how on how the different base models give the best output under which conditions. So using that, like for example, here in the meta model, which is an MLP based attention model, here attention length under heat wave condition, like TFT model performs best and gives the best accuracy. Like under morning condition in Monday, the annual hits performs best. So the MLP trusts accordingly in the better conditions. This is the model architecture. Same for the track one, all the other architectures are similar to that.
What we are seeing here is not just a forecast, it's an explainable decision. Earlier, a CNN LSTM gave one load value with a simple risk flag, no confidence, no reasoning. But in our new model, the system, let's say, predicts 412 megawatt as the bar with a guaranteed interval of 394 to 430 megawatt. This guarantee comes from conformal calibration. We collect real prediction errors on unseen data, take the 19th percentile, and that becomes the interval width. Alerts now fire on the upper bound, not the point forecast. So even if we predict 32 megawatt, but the upper bound hits 42 megawatt and the threshold is 30, then the alert still fires. That reliability doesn't exist before. One addition that wasn't in the original model is the consumption profile. It is shown here as 60% residential, 30% commercial, and 10% industrial. drawn from the profile file which was in the dataset. This makes the prediction location aware because residential, commercial, and industrial location each have fundamental different load shapes across the day. Now, instead of fixed decision tree thresholds, the meta model now dynamically weights TFT as 52%, autoformer as 28%, and N hits as 20%, shifting with conditions. Let's say on Monday morning, with rising temperature, pushes more weight to TFT because it handles long range demand patterns better. This weight dynamically keeps changing. The demand drivers explain why 412 megawatt, not the seasonal average of 310 megawatt. Temperature alone drives 42%, morning peak 30%, price effect 18%. And because solar and wind are now forecast as separate tracks, net load comes down to 32 megawatt, which only the gas backup needs. This shift from our original model to this one means operator no longer receives a number and guess what to do with. They receive a confidence bounded forecast, know which features drove it, know which model was trusted and why. And now exactly how much gas to schedule every output is self-explanatory. And that is what makes it deployable in the real world. Thank you.